Hello and welcome to my Lab 4 presentation. My name is Tyler and I will be discussing the magnetic braking with Faraday's law. The purpose of this lab is to investigate how a falling magnet induces currents in a conductive tube and how those currents create magnetic forces that slow the magnet's motion. To start off, for the important equations used throughout this lab, the most important two is the momentum principle as well as magnetic flux. And then also with that, the magnetic force. But the momentum principle is very important because we'll be dealing with Earth's gravity and the magnet falling through the center of the tube. And then the magnetic flux, obviously, it has to do with the current induced in most of the magnet's principles. And then later in the lab, it is also important that we will use Ohm's law in regards to resistivity. And as always, conservation of forces. To start off with a lab procedure, first we need to measure all the dimensions of the aluminum foil tube as well as the magnet and make sure to put that into our model. And then second, we'll conduct the experiment. We'll drop the magnet through the center of the tube and record a video with motion capture and measure the start and stop times right when the magnet enters and exits the tube. Next, we'll enter the same values into GlowScript and then we'll compare the velocity versus time with a graph, and then we'll see how that compares with our real life estimate, which is our last step. And then also note any differences and any sources of error present. So for the experiment, we need to drop a strong magnet through the center of an aluminum foil tube and see how long it takes to fall at the other side. Quickly, here's a little demonstration of what it looks like and how the magnetic field is generated through the tube. I like this right picture. I found that online. And then the left one is a little bit more of a better diagram, just showing you exactly what's happening. And then for my experiment, the 5 times it was supposed to be conducted, I got roughly almost 2 seconds each time. And then now we need to compare this with our GlowScript models. And first off, I'd like to note that there were some assumptions made in the GlowScript model. There was no air resistance. There's only 2 forces acting on the system, Earth's gravity and the magnetic force generated by the magnet falling through the tube. Also very important to note that everything is treated as static except for the descending magnet. This reduces everything basically just to the force, or just to the magnet falling through the tube. And then finally, the cardboard tube has negligible effect on the actual experiment, so that's not considered anywhere. For the GlowScript code, first off, for some important things in the GlowScript code, the length of the aluminum foil tube was about 12 inches, which is 31 centimeters. And then the width and the inner radius is shown on the left, and then as well as the mass of the magnet on the right, and then the mu magnitude of the magnet. I think I'll go into this a little later, but I think this is where I had some sources of error was with my mu magnitude. And then continuing with the final part of the GlowScript code, nothing really of note here. This is the most important part with the GlowScript code is the results. First off, the system is the bar magnet in the full tube, and in the surroundings is only the Earth. When the GlowScript code was ran, I got about 3.1 seconds. This was a 172% difference from the actual results. And then, on the left, I just showed you the north and south, and the magnets are demonstrated with the blue and red. Just because the calculated one on the top just shows you what it is at the bottom of the tube. But yeah, as you can see, towards the top of the tube, it decelerates once it's dropped, and then it reaches a steady speed, and then it accelerates again once it reaches the end of the tube. Where's the error? First off, it's very hard to calculate perfect drop conditions. I guess you can kind of boil that down to human error as well. Second is air resistance. This wasn't really considered anywhere. It probably isn't significant, but it definitely would add something. And then the most probable source of error is my mu magnitude. I think it's calculated incorrectly, and I think that's why I was getting about 172% difference. But all in all, it's not that bad. It's just not great. Now for our what ifs. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So using Ohm's law, it can be determined that the resistivity were to be decreased, the magnet would have a greater magnitude of current, and therefore would take longer to exit the tube. So if it were reduced as close as possible to 0, it would take a very long time to exit the tube. Now, what if there are holes or slots in the tube? The pipe would now have interruptions in the current and therefore an uneven magnetic field. So the magnet, as it were falling through the tube, would almost like bounce side to side, I would assume, inside the tube. It's a little difficult to say exactly what would happen, but in general, there would be a decrease in magnetic force and it would be an uneven magnetic field. And then finally, as a side note, why can't we use a ferrous material for the pipe? It's very simple. The magnet, the second it would interact with the tube, would magnetize to the tube and would never fall out of the tube. Thank you very much for watching. I hope you have a great rest of the day. And yeah, have a good one.